Hello, I'm Quincy from Hackerspace Charlotte.
Benjamin, also Hackerspace Charlotte.
And 2 or 3 years ago, we did a project called Feltronics, which was a large format electronics project kit to teach electronics. And this is it. And so we're not really going to talk so much about Feltronics as we're going to teach electronics with Feltronics, which is what it was for. Ben has really enjoyed this and sort of taken it on to the next level and enjoys not just figuring out what circuits are good, but how to make the circuits easier to understand and arrange them schematically so they make more sense. And so we've been working with this radio that we're going to show you, and we're going to build to it with a couple of simple concepts, hopefully. It's pretty simple, but we're going to need some participation. So feel free to jump in and say things. If you have questions, ask. And if we don't have answers, we'll laugh at you and pretend it's your fault. But stay involved. And with that, you may have noticed Ben has armed you.
Right.
Because the hackerspace is supposed to be dangerous. So we're going to start off with.
So this is about 5 minutes I put together called Edison to Marconi, which is essentially getting from light to a simple radio. And you do have lasers. So this is kind of fun. One of the things we did, and we're planning to roll this out at Discovery Place, but you can point the laser up here. This is a very simple circuit. Just identify the components. And so this is a battery, right? This is a switch. This is an LED, and this just connects back around. So obviously, when we turn this circuit on, the electrons can flow in the circuit, right? So this is the simplest circuit, but I want to get you right away to the most important invention of your lifetime. It still affects your life. Some of you might not have been born in, 1963 or something. But the transistor, right? Wake up to a transistor, go to bed with a transistor. The transistor is really just a switch. And this transistor has had what we can only call as a predictable solid core malfunction. You got another transistor? This one lost its contact. Yes, right there. Just picked it up and boom.
Nice.
So we have no idea what kind of transistor this is. So transistors come basically in 2 flavors. I'm going to replace the switch with a transistor because that's what a transistor is. It's a switch. So something cool, if this is the right kind, I could pass just a very little bit of current through this connection here. And we don't know what kind this is. Let's see.
I know what this kind is.
All right.
Keep telling them about a transistor.
So the transistor is really critical. It's a switch, right? In order to get it to turn on, you got to just put a little bit of current into it. So, but there's a little bit of a snafu. Nothing happens until you get the voltage up to about 0.7 volts. So that's a little bit of an explanation. And then it goes through a period of high gain. And then obviously if you get too much voltage in it, it's saturated and changes you make don't really make changes anymore. So a transistor has a butter zone. Get up to 7 volts, and then it starts to get into the sweet spot. We got anything? Oh, this is going to be nice. This is going to be a nice adventure.
All right, so
in hacking.
We will troubleshoot our circuit at the same time.
Yeah, absolutely.
So one of the cool things about transistors is that they're switches, as you know. So if you guys ever played with...
you put that one right back in this one, right?
Yeah. A rheostat, the dimmer switch that you've ever used on a light. You can walk into a room and you just flip a switch and the light turns all the way on, right? Anybody ever done that? Yeah. Everybody done that? Anybody not done that? Okay. Wake up, we're here. But has anybody ever played with those rheostats, the dimmer switches that you can turn, or the new ones, they've got a little slide right next to the switch, right? Well, a transistor is like that. It can operate, you can apply a lot of voltage to the base of the transistor. That's that middle wire. You can apply a lot of voltage there, not a lot, a little bit of voltage, and it'll turn that transistor all the way on. Or you can apply somewhat less voltage and get it to turn on a little bit. But the cool part about the transistor is that the voltage on the base is way, way smaller than the voltage it controls across it. And so that allows you to do some really neat things with the transistor by controlling electric circuits with electricity instead of a person sitting there moving the dial up and down.
This is working. It's just kind of bright in here, so this is a pretty dim light. But we can put, this is a resistor. A resistor, I was thinking how to explain a resistor this morning. I figured it out. I was driving into town. A resistor is a traffic jam, right? A wire's like 12 o'clock at night, nobody's there, fast as you want, no cops, right? But a resistor is like 8 o'clock in the morning. It's just everything conspires against you to get wherever you're going. So some resistors are like more resistant than others, and some are others. But basically, electricity flows through a resistor, but not very well. but less than perfectly good. So this is a very high value resistor, which means it's really, really slow getting through. So what we're going to do is we're going to take this basic transistor. In order to turn it on, we're going to take a little bit of resistance and put just a little bit of voltage through here. Not trivial to see it in the brightness because this is not a great connection. This is a poor connection. But we are going to get a little bit of light out of our LED because we're putting some light in. Quincy, if you got like a 1K transistor, that could be a little more interesting.
I also have this, but let me go grab a 1K.
All right, so this is kind of interesting. This will be a new feature. This was invented many, many, many years ago. Selenium, I think it's made of. And somebody discovered, like at the dawn of time, that when you put light on selenium, it changes its resistance. So traffic can go and stop based on whether you put light on this little part of the circuit. So this is kind of a cool device. So in theory, so we got some light on it now, right? But in theory, if I make this kind of dark, it's going to get dim. And if you can hit that with your laser, anybody got a laser can hit that? There you go. See the signal? So if you all hit it with your lasers, the light should turn on pretty bright. So the more you hit the selenium, the more a little bit of electricity flows through here, and then it allows more electricity flow through and light up our light. So this is the basics of
there's your 1K
of electronics. We're turning on transistors. Hey, there's a real bright one. So a little less traffic jam on the 1K. We're turning on transistors, and we're turning them off. Now, I only have one transistor up here, which means not a lot of logic happens. But your computers, of course, is when one transistor turns on another transistor. And there's a really important component here, which is feedback. So when I turn on a light, this light, in theory, right, I could point this light directly at the light detector. And then this circuit would, when it turns on, make itself turn on. And that's sort of how computers start making more complicated circuits. But what we're going to explore today is something called the useless machine, which is a machine which, when you turn on the switch, engages a gear and a motor. It opens a door, and a little arm comes out, and it turns off the switch. You've probably seen them. I think Turing was a fan of Feynman, I think, had one on his desk. But this is an important concept, right? So you need something in electronics and in computers which will oscillate. Something that when you turn it on, it wants to turn off, and when it's off, it wants to turn on. Back and forth. So that's really what we're going to try to achieve to get to Marconi. So what we do is we're going to replace, this is the coolest thing ever. This is a coil of wire, and it will produce a magnetic field when we pass current through it, because that's what coils of wire do. Every wire, in fact, when you pass electricity through it, creates a little bit of magnetism. If we coil that up, it sort of it amplifies the amount of magnetism that is generated. So this creates a little bit of magnetism on the top part when we load up the first part of the coil. And then what we're going to do is we're going to take the second part of the coil, which is influenced by that magnetic field, and take the output of that as our useless machine. That will be the gears and the levers that will reach back and turn off the main switch. So when we turn on the magnet on the top part, it will have a magnetic influx. The magnetic flux will have a phase shift, and it will create a signal on the out part, which is out of phase with the in part. So there's a little delay.
Does everybody understand that part real quick? That's really important. When you put electricity through the coil, a magnetic field comes up. Has anybody played with an electromagnet before? A buzzer, a doorbell, things like that. When the electricity goes through there, the magnetic field sets up. But that magnetic field affects all the other metal that's nearby, including the other part of the coil. And so when a magnetic field moves around a coil, or a coil moves around a magnetic field, electricity starts to flow.
So this is the basic. This is how we get electricity. All the electricity we're getting here today comes here because somebody's passing a magnet through a coil.
Is that an inductor?
A coil is also called an inductor. And yes, this is an inductor, but it's a little more complicated than just an inductor because it's got a center tap and it's got a ferrite coil.
Ferrite coil.
Yeah, that's called a loop stick, I think, for some reason. So if you need a loop stick, let me know. I can set you up with some loop sticks. Yeah, so your generators with the nuclear, right, creating steam. Steam creates a turbine. Turbine spins a magnet. Magnet is passing through a coil. All the electricity that you see here comes into existence because of a coil of wire and a magnet moving through the middle. But the inverse is also true. If you move electricity into the coil, it will move the magnet. And so your motors all operate on that principle. So this contains in itself the basics of what we're dealing with in terms of electromagnetics, which is a coil that creates the magnetic field, and then immediately, we're not moving any motors or gears or anything, but immediately that magnetic field is detected on the back end, and it shoots out the bottom in the inverse in a phase delayed form, right?
There's really two coils on it?
There is. There's two coils. There's a top coil and a bottom coil. They happen to be connected in the middle. They're the same wire in a sense, right? But it's important to realize that this part behaves on its own, and this part behaves on its own. And one is up here, one is down here. The loop stick connects the two of them together. The loop stick changes the efficiency with which the magnetic field travels from one side to the other. And we can see that if we pull it out, it will change the relationship on the board. So this is important. So instead of lighting up an LED, we are going to create magnetism. So we take out the LED part of our circuit, and we put this in place. And we're going to go from here to here. So we're going to engage this little wire here to get us there.
Now here's an interesting thing to know. We say ground. Have you guys ever messed with a grounded electrical cord? It's got that third prong on it. That third one goes straight to ground. And there's a saying that ground is ground the world around. So to make a circuit, a basic circuit, you have to have a loop. You have to go from the positive battery terminal to the negative battery terminal. You have to complete that loop. But the crazy thing about ground is if I stick one side of my light bulb onto one terminal of the battery, it's not going to turn on until I stick the other terminal the other side of the battery, right? Does that make sense? Is everybody familiar with that? Well, it'll also turn on if I take one end of that light bulb that I was going to stick to the battery and I plug it in the earth, into ground. And I take the other end and I stick it in the earth someplace else. It's not so much that the earth is conducting. It can just absorb and provide all of the balance to any circuit. So ground is ground the world around. And so sort of what Ben's doing here, where he's putting this ground symbol, you can physically connect it with a wire, or it can actually be connected in the ground. And in circuits, you'll often see the ground all over so they don't have to show those wires running everywhere.
So again, with a transistor, we need to get it past its sort of sleep stage. We've got to wake it up. And to wake it up, we're gonna need to get it about 0.7 volts, a little bit of current, and that's this resistor. It doesn't do very much, but it does sort of wake it up and get it just to the point where it's almost on, just a little bit on. And when it's there, it's very easy to make it go more or less on. And we need that because we're not creating a lot of signal. OK, so now we have a battery, we have a transistor, we have a resistor. The next thing, and I think the last component we're going to add today, is a capacitor. And this is tricky. The trick about a capacitor is that it's a circuit that can be satisfied. When you start putting current in here, it will absorb it until it is full. And just like the meal you just ate, comes a point where you look at the pizza table and you say, nah, I could have the nicest pizza in the world, but I ain't eating any more. So this won't keep eating pizza. It comes to a point where it's done eating pizza. And then it has to have a change before it can eat pizza again. So it can be discharged. Never mind the metaphor. But it can be discharged and it can be filled up, right? But it can't just constantly absorb new electrons. And so it's shown with an isolation, and it is an isolation. But interesting things happen. It kind of creates this interesting way in which signals can be passed from one part of a circuit to another part of a circuit without undue influence on the circuit. So we just want the signal. We don't want the other aspects that are going on. It's kind of like buying a company out of bankruptcy. You just want the assets. You don't want all the liabilities. And so this creates an insulator that allows you to get the signal you want without creating the drain and the path to ground, because that's a problem. If you create a path to ground, all of your electrons will just leak out, right? So we have here a pretty good path to ground in our coil, and we want to protect ourselves from that.
So hang on a second. The schematic symbols, just to help you understand, this is a capacitor. The wire doesn't go straight through like it does on some of these shorts and things. It stops, right? And physically what it actually is in there, there's a metal plate, usually metal or something very similar, and there's another one like this. And so it gets really close. It's like if you're trying to plug in a tool in the garage and the cord's just not long enough, it gets close, but you don't connect. So electricity can't flow. So one of those plates can feel the electricity on the other side, but the electricity actually can't cross if it just stays there. It can feel it, and it wants to move, but it can only go so far, and then it just can't physically go. But if you switch it, it can keep feeling it. And so that's why you're not going to leak electricity across the capacitor, unless...
So whatever happens on this side happens on this side, but it doesn't actually flow through. So if we fill this one up, this one gets excited. If we empty this one feels empty. All right, so again, we're creating a load on this side to create a magnet. The magnetic field will cross over and create a signal. The signal, and only the signal, because we have a capacitor, is going to pass into this junction. Now this is an important junction right here. This is the business end. This is where all the decisions are made. It's a very sensitive part of the circuit. If I touch this, this will probably change its behavior, because this is just barely on, and it's very easy to manipulate, and it controls the rest of the circuit. So at this point, there's a good chance that this circuit is already running. I say a good chance because I can see that it's not. All right, so we're biased up. We had to change the transistor. Well, you gave me the other transistor, right?
Switch your capacitor. Try this one.
OK.
To see if it'll couple it better.
Oh, you know what? This is this in the right way?
That's
it
right.
Is. That's positive.
Yep.
OK. Oh well, we could probably connect the probe to the. So, list of things to check when checking is whether or not the probe is connected to the output. Yeah. All right.
Master of the obvious.
Yes, yes. This is actually an issue with Feltronics, is that in order to use this in front of a live crowd, you have to be able to troubleshoot electronics. Dead.
Connect the probe.
Well, yeah, but it could have been any one of these 30 connections, right? And so, or any one of these parts being flipped the wrong way, right? There's many ways to do this wrong, and like exactly one way to do it right. It's a bit of an issue that way. So it is happening, right? So we're loading this. This is transmitting.
What do you mean when you say loading?
So what we mean when we say loading is we're drawing a current through a device, and we're creating the magnetic field. We're detecting the magnetic field. It's passing through the signal here, and this is a radio. The only problem is, how come it's not telling us what the frequency is? All right, it's at 1.6. Don't tell the FCC. It's at 1.6 megahertz.
That's fine.
Is it within reason? Can we reach it?
Yeah.
I don't think so.
Yeah. 1.7.
Oh yeah, we can go that high. Okay, so we're legal.
We're good.
We're in the AM band.
I have a ham license.
All right, so what we added now, one more item we can add.
Maybe not after this. Yeah, right.
There's a really beautiful circuit called the tank circuit, and it's beautiful because it was discovered by, I don't know, Tesla or his gang years ago. And they didn't have oscilloscopes. They couldn't see what was going on, and they were able to make these circuits without seeing them. Of course, they didn't have to do them in front of a live audience, but they were able to do it without oscilloscope.
And the tank circuit, it gets its name from like a water tank. If you've ever been in a bathtub or anything and you slosh the water, you can make it slosh, and you give it just a little push this way, and then it kind of dies down after a while. But if you push it at the right time, every time, it'll slosh back and forth. Well, a tank circuit is going to be that sort of thing with electricity. The water's going to slosh to one side, the electricity is going to go one way, and then back the other way. Because if you remember the parts about the capacitor, or the inductor, which we may not have covered quite so much, the capacitor, it's gonna feel the electricity, but it can't get there, right? The electricity wants to get across that gap to the other side, but it doesn't have a path to get there. And an inductor, this coil is just a coil of wire. Has anybody had a coil, a long extension cord coiled up in their garage, and they tried to plug in a tool and it was just too short? So they saw the extension cord over there, and they grabbed the extension cord and they plugged it in, 100-foot extension cord to go 2 inches, So an extension cord, even though it's still coiled up, still passes electricity through it. It's a short. And if it's DC electricity, like a battery or something, it's like, have at it, keep going. It's the highway. But if you change the electricity, when the electricity changes, that's the load we're talking about, it creates this magnetic field every time it changes. So the first time the electricity goes through, it has to work hard. It has to push. That's a load, like a horse pulling a carriage. It's a load. These people, when they were doing electricity, lots of horses. So it was a load that you were establishing there, and it's doing work. And so it goes easily through the coil if it's DC, but it doesn't like alternating current. It doesn't like it when it changes very much. It has to work each time. And so the capacitor is sitting there, and it's got this charge on it, and it wants to jump to the other side, but it can't. But how can it get to the other side? How can the charge on this plate get to this plate? And the answer is it can go through the coil and back to the other side. But when it gets to the other side, is it ever happy? No, it wants to go the other way. But what's fighting it the whole time? The coil. Every time it changes, you get this magnetic field that sets up, and it's like, hey, thanks for all the work. And then it collapses, and it keeps pushing it around, and back to Ben.
So to make a longer story shorter, this is a variable capacitor, and it just defines how much pizza you can eat before you really are done. And if we just create a larger area, it will slow down the frequency. And if we make a smaller area, there are plates that are interfacing each other like this, then the frequency will go faster. And that is how you tune a radio. That's how you decide whether you want to listen to or not or whatever. So
and the dial on your radio is really connected right to a capacitor.
You're not on your grandmother's radio.
Yeah. Sorry, not Pandora and not modern, but.
All right. So once we have this radio, we should be able to turn this on, and we should be able to find this frequency, and we can probably hear it come in. Hear that nice old-fashioned radio sound? But I'm changing the transmit frequency, not the receiver. So we're definitely in there. We can add a switch now here. It doesn't hardly matter where, and we can kill it. We can kill our transmitter. It's nice to have a memory scope because when you kill it, it doesn't die. It's just like, oh, I'll just hold this for you on memory. Yeah. Okay, so that's Marconi. Marconi was able to talk to ships at sea and to different continents using essentially this principle. He didn't have a transistor, so he had a little bit of a larger hurdle to jump. But essentially, he did have this, and a tank circuit, and all the rest. But this is how we managed to connect continents for the first time.
But these components are really, really simple. I mean, this is as basic as you get in electronics. A resistor is just the thing that opposes the flow of electricity, whether it's a light bulb or whatever. It's been around forever. The capacitor, again, it's just that plate. So very simple. If you wanted to make those on your own, you could roll up aluminum foil with some wax paper in between, and you end up with a capacitor. A coil, we actually made these ourselves. We just wrapped paper around, or we wrapped paper around a tube of the right size, and then wrapped wire around that. And that made the inductor. So very simple things. Transistor was a little bit more advanced, but it's in everything. Like, how many transistors are in this room right now? Billions, trillions, right? So an enormous number. But, keep going.
Well, just a fun note on this circuit. This circuit came to us with a couple extra parts, and we actually got to get rid of some parts. So it's an original circuit just for Feltronics. That's kind of a fun thing.
So it's as simple as it can be, and hopefully no simpler.
I think it's simpler. We can't get any simpler. We really tried.
But the idea here is that electronics isn't that complicated. There's not that much. With this, you can communicate around the world. You want to step up the power, and you can clean up the signal. If you adjust some capacitors and change the values and add some more, it gets a little bit nicer. You can add in a microphone to turn this on and off, separate from just all the way on, all the way off. You can vary the amplitude so that you can actually carry speech instead of just Morse code over the radio. So they had something as simple as this. They tweaked it and started doing more and more complicated things. But it's not that complicated. The ability to communicate around the world is just not that complicated. And so we were hoping to help you guys get to that point, see that realization. But what part of it doesn't make sense is what we want to know.
Still not sure what a transistor really is.
Okay, so the transistor, this little guy right here, outside of this circuit, right? All that we're doing is turning it on. So if you recall me talking about the light switch, right? Here, we're going to add a few numbers. We've got 6 volts here, right? And this is the total power available, the total voltage available to my transistor. And what I want is I want this wire here to look like, to turn something on with the transistor, I want to turn my transistor into this, where it's just a short, right? And that's what I'm trying to get to. When I turn my transistor on, it becomes a short. And when I turn my transistor off, it's an open. No electricity passes, all right? And we control that through the base of the transistor. This little middle guy right here determines how easily electricity can flow. And when electricity flows easily, then the transistor's on or saturated.
Like a variable resistor?
It's very much like a variable resistor, except a variable resistor is controlled how? Through physical motion right? I'm moving a swiper across the conductive or resistive material to establish how much resistance is present in that resistor. In this one, we do it with electricity. And the inner workings of a transistor.
I didn't know that a variable resistor was a real thing. I just was maybe.
There are several versions.
Yes.
And resistance is not quite the metaphor. It's really not about resistance. It's more like traffic lights. There's very, very weird things happen at that scale. It's very small. And there are several kinds of transistors. The FET is the one that you're using more, the field effect transistor. It's much more efficient. This is just a bipolar junction transistor. And there are different ways of describing what's happening, but basically when you put pressure in there, it opens the valve, kind of like your sprinkler. It's current sensitive. There's the game on this one where every time you send an electrode from here to here, like about 1,000 can go from here to here, but not more. So if you add 2, you get 2,000. If you add 5, you get 5,000. It's kind of like this fixed relationship.
The battery as well to give it some power enough to allow what you need through.
Right. Yes. Absolutely. So the one thing that transistors are used in amplifiers, right? They amplify a signal, but people tend to make the mistake. It's like if I've got a 6-volt battery here, I'm going to amplify that and get like 100 volts. Well, no. What you're going to do is you're going to take a small signal here on the base, you know, whether it's a really tiny signal, 0.6 volts, or smaller, or bigger, or depending on what you're doing, but you're going to take a small signal here and amplify it up to the available power, which is 6 volts in this circuit here. So that's what the transistor is doing. And the way that it works, there's some material. Have you guys heard of silicon? Right, so we use these semiconductor materials that kind of conduct, and we add a little bit of electrons to some material, and we take some electrons out of the other material, and then we sandwich that material. So there are 2 of one type and 1 of the other in the middle. And what we do by adding electrons or taking them away from this bottom material is we make that region in between that's blocking the electricity from getting from one side to the other, we make it smaller. And as it gets smaller, then more electrons are able to jump across. And that's a terrible way to try to describe transistors and diodes.
Another way to think of that is if you're trying to get across a river, you've got these little lily pads, right? And if they're too far, you can't jump because you can only jump so far, right? But you've got other lily pads left and right. And if you squeeze the lily pads together, you can create like a path in which each step is close enough that you can get through. So you're taking a little bit of energy and moving the lily pads close and kind of crowding them. And then it creates this opportunity for the electrons to jump across. And then when there's no field, they relax, and then it's too far. The distances literally are too far for the electricity to jump across. So if you raise the voltage, you can get across, and the very other things. They break down voltages and so forth. But that's really what's happening is that the distances are opening up. Electricity can't pass over. And then you crowd it up. And the crowding is happening just by putting a little bit of current in the other places and creating a field effect, it's called, in an FET transistor. A little bit different in a bijunction transistor.
You wanted another analogy?
Yeah. Actually, I was going to say the metaphors aren't helpful to me. So
okay.
It sounds like what you're saying is inside these tiny little things that you have on your circuit board, there's not moving parts, but the materials that we choose to put inside these tiny, tiny things expand and contract. Is that accurate?
No.
The movement is at an electron level, right?
Right. So
you don't think of it as movement, but it is.
But how did anyone figure that out before we could even look at electrons?
They observed behavior on a larger scale, and they said, wow, that's interesting. What happens if I do this? And they just tried stuff, and it was sort of the trial and error. And they said, well, I know what happens when I do this. I don't know why, but I know that it happens, and I can do something useful with that. And so they started to apply it. And then, as we had the transistors, they were able to look a little closer. So they started figuring those things out. But the radio, the very simplest of radios, radio receivers, are so simple that troops in the trenches were able to make them using a razor blade, a pencil, and an earphone, right, and a wire for their antenna. That's all they had available. They would do this in prisons and such when they were captured. And that's all that it takes to rectify a radio signal. And they didn't need to know exactly why it worked, but they knew that it did. Sharpen that pencil and tune your radio.
Have you seen Nicholas Tesla's picture?
Yeah. Yes, sir.
So can we go through what the transistor in this circuit is doing from the point where we turn it on and so forth?
Yes.
Again, because like you said, the analogies are not necessarily what
All right, this is good to know.
Yeah, it's tough. That analogy with the lily pads, that was really close. If you reduce that down to a microscopic level, you get really close to what's happening.
Stop with the analogy.
I don't have a microscope. I mean, you need like a tunneling microscope to see this stuff.
It really is. So one thing to remember in electricity, right? How fast does electricity travel?
Why do you need it here?
Well, he's setting this up. Huh? Nearly the speed of light. We just call it the speed of light. It's pretty darn close. A little bit slower because it's not in a vacuum and some other niftiness. But speed of light. How fast do electrons move? Walking speed, running speed, right? I mean, like if you were to flip on that light switch, you could run to the light and take it out before the electrons got there. Now, really, that's because it's alternating current. They don't go very far before they switch directions. But the electricity travels a lot faster than electrons move. Imagine, for another analogy, this one we might be able to hang on to. With electricity, whether it's DC or AC, if I've got a garden hose and I've got a bunch of marbles that I've piled into the garden hose, and the garden hose is full, the electrons are in there. If I pop another marble into the garden hose, the marble's going to pop out the other end. And if I keep popping marbles in, they're going to keep popping out the other end, right? Almost instantaneously. The instant I pop one in, one pops out the other side. Does that make sense? But the marbles themselves are only moving so fast through the garden hose. It's the same thing with electricity. And with alternating electricity, I pop one in, and then I pull them back and I go back and forth. So the electrons are shaking around inside of that wire, inside of that hose, but they're not really moving so far. They're just doing some work. And so he's plugging on. Let's see. Yes?
So just to clarify, I'm sorry for beating a dead horse, but the people, you guys made it sound like, you know, intercontinental communication was really simple. The people that invented this, you're saying that they had no understanding of the material science. They're just like finding things and plugging them together, and like that works.
I mean, with most scientific discovery, they observed something in the world around them, and they experimented. And so to say that through their experimentation and what they learned, they didn't know anything about the material science, I mean, they were discovering that science, right?
No, I think you make a good point, which is so interesting because the diagrams that we use today, like this arrow, were completely developed, and it wasn't until later that they realized that they were all going the wrong way.
But being engineers and practical, they said, we've already written the books with the arrows going this way. We're not rewriting them.
Yes.
And so they kept the arrows going the wrong way, which really hurt my head.
It's totally true that they didn't understand the material science. Absolutely. The answer to the question is completely, totally had no clue what was happening. It was all observed, and they were just tying observations together. This works when I do this. This hurts when I do that. Don't do it, right? It's all. They were playing with crystals. I mean, they were putting electricity on crystals, and they discovered rectification, which allowed for the, you know, it would flow one way through a crystal, and then it wouldn't flow back the other way. Things like this. There are certain crystals that they found only in certain people's backyards that had other rocks that were deposited with them, and so this natural doping, and doping means you interface with the material. It's like on the elemental table of elements, right? But it's influenced by other things, and it creates impurities called doping. So there were crystals that are on the table of elements that were next to other rocks in certain backyards, but like in another country, the same element wouldn't work. And it boils down to like it was in there with other things, and those impurities got in and created this. So it was the discovery of these semiconductors, I think, was largely, as you say, no idea what's going on, accidents happen, people like putting probes onto different rocks and seeing what they would do. And
that said, they reached this point where they actually had some idea about some of the theoretical possibilities. They said, well, if we could get that behavior that we think will happen, we can start doing these other cool things. And so they had some idea about what they would do with transistors and how they could make transistors behave, how they could use them, before they actually were able to construct them. And so they sort of reached that tipping point where it's like, okay, I've observed these things. I know what I can do if I can reliably control that, but how do I do that? And they didn't come to that right away. So more voltage.
So back to the transistor. I like to do this with my hand. I couldn't do it with the voltage, but when I put my hand on here, the LED lights up just a little bit. And I do it with my hand because everybody knows that you don't conduct electricity with your hands, right? You have a sense that this is like a really high amount of resistance. So very little bit of energy going into the base, and I am actually able to get a visible light out if I add this 1K, it's brighter now because I upped the voltage. I'm able to get something you can see. So if I take this same 1K, this traffic jam, right, and I were to use it to power the LED directly, it would, I mean, it's turning on, but you probably can't see it, right? So the difference between that amount of light, which is like just enough that I can barely see it.
Does anybody want to come up and look if they doubt us? Or
no, it is turning on.
Even if you don't
bit,
doubt us, if you just want to affirm to everybody else, it's all
But
right.
if I now turn it on with this, right, that's the same amount of electricity roughly going through there. But for every one electron that gets through there, I'm getting a lot more electrons that pass through the switch. So that's the observed behavior, and that's really all you have to go on.
And so with this transistor, just the value that it is, it's 100 to 1 gain, which means for every electron here, 100 going this way. So that makes a big difference.
But for here, for this circuit, it doesn't matter. We're just bringing up an LED. You wouldn't need to design your circuit that way. Let's go to the radio example.
Okay. All right. Well, so you're comfortable with the idea that when I apply the voltage here, it turns this on. I have the voltage on this side over here on this side, right? And when I take it away, it turns off. So on and off is controlled right here at the base. That's the part that you want to hang on to.
Yeah, there's one more thing we can do here before we go to the radio. The radio
Making you work for
oscillates
it.
really fast, and it's hard to understand what's happening. But what I want to show before we get there, right, is that this junction is now very sensitive. In other words, it's on, it's right in the butter zone. It's not as bright as it could be. You've seen it brighter, but it's not dark either, right? So it's right there at 50-50, which is kind of what you want. Then what you can do is you can make very small changes that will throw the signal up and down. And that's really where we're going with radio. We want to get that signal going up and down, right? We want to get the thing like a teeter-totter. So what we have to create is like a teeter-totter, something that's balanced on a knife edge. Once it's balanced, then little changes, right, will start it swinging.
So you're looking for an oscillation between two, not extremes, but two fairly particular variables in your resistance.
This is a sine wave oscillation, right?
You'll see on the scope that when we go beyond that, it'll clip. It can't go anymore, and it'll stop. And so it starts as a sine wave, and then it stops and goes across. And in music, you kind of hear that when audio clips and such and sounds terrible. And we'll get essentially the same thing in a radio.
So this is kind of interesting in that I've inverted this so that when I nice, I got the dead one.
Laser, anybody?
No, I got two. Maybe one will work. Okay, so when I put power on this, it turns off, right? You see that? So that's an inversion. So that's because I have this on the top side of the junction, and I'm pulling it. Essentially, I'm pulling it up by adding light. If I move this to the bottom side, in other words, the ground, I've already pulled it significantly, right? Because this does flow. Of course, if it's darker, it flows less. And then I can add. But now when I turn this on, it turns on. So the point is that I can manipulate this point up or down by very. This doesn't change a lot. Very subtle means, and create a change in the output. So now what I want to do is I want to create a situation where this thing itself is driving this junction. So this load is driving the junction. This is an LED, which is a kind of thing I can use. I can use this to feed back. But if I did, there's no phase difference, there's no time delay, and it would kind of happen immediately, and it would just come to a static understanding of where it would come to a stasis. It's because this has a phase shift that it can never settle on an idea.
It takes a while for the magnetic field to set up, and the magnetic field in one side of the coil is delayed setting up from the electricity that's going through the coil, and that magnetic field, when it sets up in the other side of the coil, induces electricity, which is also delayed. So that delay is what makes the radio work. And how
You're an inductor, or in this case, you were calling it something else.
Inductor is fine.
Inductor. So in this case, your inductor is creating that slight variation, and the amplification is coming from your transistor.
Yeah.
Yes.
The signal coming out of the bottom of this is much less.
So you could theoretically have a much bigger inductor and do it that way.
What do you mean?
Well, if your inductor was able to handle a greater amount of current.
What could you do with that?
Instead of having, or are you needing the inverse of that?
You really need it. You need amplification in order to create a self-driving oscillation.
Because it's feeding back on itself?
Yeah, because the signal out will never be greater than the signal in.
There's always loss going through this.
So it's feeding from the inductor back through the transistor,
right.
And then, okay. I couldn't see the circuit.
Oh, yeah.
So I moved.
Sorry.
So just to finish it, we're going to replace this LED with the top half of the loop. So now we're powering this top half of the coil instead of the LED. Everything else is the same circuit. Get that out of there. And we're going to take the bottom half of this, and we're going to feed it in directly into there. So this bottom half drives that, and the top half is driven there. I should already be oscillating.
Yes.
Am I, in fact?
Yes.
All right, so that's it. I mean, it's a pretty small change, right? We just went from an LED to this double-headed thing. We're driving the top part as the load, and this is feeding back. So this is tickling the base, and the base is changing the current on the top side. And it's pretty significant. I mean, we're kind of going rail to rail. I mean, we're crashing on both sides there. You can see it's
not a nice smooth curve.
So so does that make sense? This was really cool because this was stuff I did as a kid, but I gotta be honest, I didn't understand it when I was a kid. Anybody can do paint by number, right? But when you get to the point where you can actually like choose the colors and manipulate the design and change it in ways, pull out a part, say we just don't need that part, right? Then you're starting to get to a different level of understanding it. So it's our view that kids should learn this stuff. They should learn it well when they're young, so they have a foundation. When they're older, I mean, they're using billions of transistors and have no idea what they're doing, right? At some point, we run a risk of being consumers of technology for which we had no understanding.
Right.
And I think we're already there.
Yeah. Well, but the thing is that right? One of the things we did is we brought in just some old circuit boards, right? And just you can look on here and say like, well, those are capacitors, these big round things, and I can see they've got inductors on here. And here's this other inductor with the toroid. It's got the ferrite core inside of it. And here's a transistor, and here's a transistor, and here's a transistor, and resistors all over the place. You could pull this apart and put together the same thing. Now, the one sneaky thing that we have is the ferrite, but this one even has the ferrite core conveniently. So transformers, those are the things that it's just the inductors, right? And this is what we actually use when you plug in those wall warts to charge your phone and everything, because you induce electricity on one side in one coil, and that induces electricity on the other side of the coil, that electricity does. And so you can change the voltage by changing the number of coils. The ratio of coils on one side of the transformer as opposed to the other side changes the voltage. And so inside of all of those, you've got transformers that you can pull out and start making radio. So it's all around you, and it's just not that complicated. So hopefully, you can, if you take just a little bit of time to play with it, you can see that. And so what Ben's doing now is moving that ferrite core in and out of the coil, and that changes how the magnetic field is able to pass from one coil to the next.
So when I drop it out of the bottom, there's no loop stick in the top. It makes it go much faster because I think there's no resistance to the magnetic field setting up. It's not being asked to create a magnetic field in the loop stick anymore, and so it just sets up immediately because there's nothing there in its way. And if I pull it out of the top, we lose almost all amplitude and no frequency shift at all as I pull it out of the top. It's still having to do the same amount of work on the top, but lesser and less of the signal is getting through to the bottom as I pull it out of the bottom. So you can see how the loop stick contributes to the behavior.
The magnetic field and how it transfers the magnetism from one coil to the next is a difficult one to do without like pictures and video, and I didn't see anything like that, and analogies. And I'm no artist, so I have failed miserably in that regard. I apologize, but
well, the felt electronics is simply is a lot more helpful than a breadboard.
Yes. Well, so the other thing that I wanted to make a radio so we could tune our circuit. And this is this is the old way, right? And where all the components are on here, and you just use wires from here to there.
But everybody should recognize that circuit because it's a real common circuit. See, you recognize this circuit, everybody?
Yeah, this is. Yeah, that's.
See,
there's no hope for this. So.
And you learn nothing, right? It's spaghetti.
Yeah, and so that was the idea behind Feltronics. We wanted you to be able to see it, understand it, have it look a little bit more like the schematic in the book than just a bunch of wires run around. So hopefully it makes it a little easier.
So what's next for the project? You said you're going into Discovery Place?
Yes, we'll go to Discovery Place and teach them some of the basics and make sure that they understand what a resistor is, what it does, how a capacitor works, a couple circuits with capacitors, inductors where they'll do electromagnets, and they'll actually make that magnet, the buzzer where they push the button and it clicks over, and they can pretend like they're sending Morse code, and then to the radio where we'll actually have them transmit from one felt circuit over to another felt circuit. So.
Is that going to be a permanent display there?
It's not planned at the moment. Right now, they just have us come in to do dangerous science, and so you hand lasers to kids, and it's dangerous for sure.
So one thing we're working on is trying to figure out how we can build it. Right? It's very labor-intensive to make the parts.
Yeah.
And the next thing would be teaching people how to use it. It's not trivial. It's not. Teachers are great people, I'm sure, but honestly, I'm pretty sure I could take any school in town and not find anybody who could do this in your average school. It's non-trivial work.
That's part of the problem. If you have a very concrete set of circuits, you can have somebody assemble it. And my son was just playing with snap circuits the other day, and he was able to put it together and go through the book. And what do you know about that? Not much, right? He could do it, but he didn't necessarily understand it. He didn't know what would happen if he would change this component with that component, or was that one essential? He knew he could put in a bigger resistor, and that might make it go faster or slower depending on where he put it, but he didn't really understand it. And you need the understanding to really help the kids explore, because kids are going to ask those questions, right? They're not going to hesitate to say, well, do I need that capacitor there? Why can't I just send the electricity straight into the base of the transistor? And the teacher's going to be like, well, because it's what's in the teacher's manual. And so we either need to figure out those circuits that that slowly help the teachers learn along with the kids so that they can do that, or that don't allow them to step outside their own comfort zone, even as the kids ask questions, so they're staying in there and they're able to answer the questions and help the kids grow in their understanding. But at some point, really quick, and that's what we're trying to do with Feltronics, is really quick we want to get them into the unknown where you can do all sorts of crazy stuff, because you can really fast, you know, and so it is tricky, and just having teachers do it is not as easy as it sounds.
Well, any other questions for these guys?
So I just want to leave you with this one circuit. If you have a microprocessor and you don't need to do much complicated circuits, but you do want to drive a load, you need a circuit that looks like this. Transistor on the bottom, load on the top, anything can be your light or a motor or anything, and then you just drive this middle part with your microcontroller, and then you can make all the big stuff move. So this is like,
if you've got Arduinos.
Because computers have really replaced all of this. We don't do all of this in analogs, right? But you just need to know this, and once you know this, you can do a lot with a microcontroller. So.
Thanks, you guys.
Thank you very much for having us.